So I'm Yuichiro Ueno, a geochemist from Tokyo Institute of Technology. And today I'd like to stimulate the discussion about the chemical and the chemistry of the early atmosphere, early Earth's atmosphere, and also mention about the early Martian atmosphere too. And this slide is already shown by the previous speaker, David, and basically the same slide. But I think the most important thing of this figure is this question mark. So it's very, very difficult to quantitatively estimate the chemical composition of the atmosphere 2 or 3 billion years ago. So many people argue that the carbon dioxide is the main component of the early Earth's atmosphere instead of oxygen before the emergence of photosynthesis. But so many things are unknown. So the speciation of carbon, for example, methane level or carbon monoxide level and so on. And but we can see something changed through time by using the stable isotope. I'm a stable isotope geochemist. This is the carbon isotopic ratio through time from 3.5 to 500 million years ago. And we can see the organic carbon, sedimentary organic carbon is depleted in C13 compared to the carbonate carbon because of the photosynthesis preferentially fixed the C12 against the C13 a little bit. But at the time period from 2.8 to 2.5 billion years ago, we call late Archean, we can see the unusually white organic carbon in the sedimentary rocks. So something happened in this time period. So the first, the two theories, one hypothesis to explain this isotopic anomaly is the global methanotrophy scenario introduced by John Hayes in 1994. And because the very isotopically light methane can be metabolized by methane-consuming microbes. And then methane is a gas, so doesn't incorporate in the rock record. But if methanotrophs are eating isotopically light methane into the biomass, that is solid material, and recorded in the rock sample, and that's why we can see this isotopic anomaly. So many people argue that in this time period, the late Archean atmosphere was rich in methane. But the second scenario, introduced by Jim Casting and Alex Pavlov, 2001, if the methane level is high, and then this is polymerized into hydrocarbon haze and could be deposited directly in the ground, that can be make this isotopic anomaly. So both cases, this time period, several geochemists argue that the methane level is high. But I would like to introduce third scenario instead of these two. And how to monitor the chemistry of the atmosphere. And that is the sulfur isotopes. And this isotopic anomaly not only can be seen in carbon, but also in the sulfur isotopes. And this sort of isotopic anomaly can be produced only by the photochemistry happening in the gas phase, in the atmosphere. And so, and this signal is disappeared after 2.4 or 3 billion years because the atmospheric oxygen levels rise. And then, the isotopic anomaly was produced by photodissociation of sulfur dioxide by ultraviolet light. But after rise of oxygen, the sulfur entering into the atmosphere is totally oxidized into sulfate. So we cannot see the positive and negative isotopic anomaly. So the zero means the mantle or volcanic input. So the disappearance of this isotopic anomaly is interpreted as a very strong sign of the rise of oxygen at about 2.3 billion years ago. So the presence of this anomaly means the very low level of oxygen, say less than 1 ppm or even more less. But we can still see the change of this signal through time, even before the rise of oxygen. And also, the sulfur has a 4-stable isotope. This is a isotopic anomaly for sulfur 33. And the y-axis shows the sulfur isotopic anomaly for sulfur 36. Yes. And then both two anomalies can be produced by photochemistry in the atmosphere. And yes, we can make this sort of isotopic anomaly in laboratory by simulating the photodissociation process of SO2. Yes, these blue dots are the experimental results. Yes, we geochemists succeed to produce isotopic anomaly. It's very rare. And but the problem is this red data point is the geological record. So the interpretation is like this. You know, the volcanic emission has no anomaly, but in the atmosphere, the photochemistry produce reducing sulfur species, and remaining SO2 is further oxidized into sulfate, oxidizing sulfur species. And both two positive and negative isotopic anomaly is carried down into this, ultimately into the sediment. But none of these data point is here, right? That's a big problem. So what's wrong? And we trying to reproduce this number by changing the chemical composition of the experiment. And we found that the big problem is if we put SO2 into the chamber, it's the redox states of the atmosphere is very oxidizing. Because once you photolyze SO2, and then always we created excess oxygen atom. It's a very oxidizing condition. Far different from the reducing early Archean atmosphere. So that's why we trying to scavenge this excess oxygen by putting carbon monoxide into the system. All right, and then yes, we can reproduce the numbers. So the chemistry is very key to interpret this isotopic anomaly created by the photochemical process in the atmosphere. So based on this our experimental result, we argue that the both magnitude and the ratio between the two anomalies can be changed by two factors. One is the partial pressure of SO2 that might monitoring the volcanic flux, and also the redox states of atmosphere, or the amount of carbon monoxide against the carbon dioxide. Okay, so we argue that the percent level of carbon monoxide was present. Otherwise, we cannot reproduce the data, geological record. And also, the carbon dioxide, partial pressure of carbon dioxide should be less than 0.1 bar. Otherwise, the atmospheric condition is very oxidizing, and it's not suitable to preserve the isotopic anomaly. So now we argue that the late Archean time period is the atmosphere was rich in carbon monoxide, not only CO2. The early Archean atmosphere is not 100% CO2. Okay, so if our model is correct, even before the rise of oxygen, redox states can change, and that can be traced by the ratio between the two anomalies, and also. If we look at the magnitude of the isotopic anomaly, rise in small and large and small, and then disappeared. That may suggest the intensity of the subaerial volcanisms. That is consistent with the previous geological record, because we know that this late Archean time period is a lot of banded iron formation was produced, can be seen. That suggests that the higher ferrous iron flux into the ocean. That means a higher hydrothermal activity. And also, this is the age population of the zircon or granite. So yes, we can see the this time period, the island archetype volcanism is very, very high. So maybe this the huge volcanic activity supply the reducing power into the atmosphere and ocean system. That may be the reason why this time period is very reducing. So I know not all people believe my story, rich in carbon monoxide. But what is the source of carbon monoxide? The most plausible source is the photodissociation of carbon dioxide. Okay. CO2 is always photolysed into carbon monoxide. And sometimes there's carbon monoxide back into CO2. If the most efficient way is the oxidation of OH radical that is produced by the, again, photodissociation process of water. That is the most efficient way to oxidize CO back into CO2. But if the higher volcanic activity supply reducing agent to scavenge this OH radicals, hydroxyl radicals, and then CO level can be increased. And as a consequence, iron oxide can be deposited, like we can see in the deposit of BIF. So that is expected scenario, but how to test this model? So we trying to measure the isotopic fractionation by this process for the dissociation of CO2. So what kind of isotopic fractionation happen? The experiment is very simple. We use the solar simulator, the UV source that has a similar spectrum of sun, and put the CO2 in the flask with the UV window and photolyze into CO. And the excess oxygen in this system is finally go into O2. But in nature, this oxygen is scavenged by reducing agent, hydrogen, iron, or somewhere else. But anyway, and just to measure the isotopic composition of product CO. So, and the result is very surprising. And we determined the isotopic fractionation by photodissociation of CO2 is more than 100 per mole. And this is the product isotopic ratio of product to carbon monoxide. It's minus 130 per mole against the initial CO2, carbon dioxide. And this is a very surprising result, but is already predicted by theoretical calculation. This is the work published by my colleague in Denmark, Johan Schmidt. He used the ab initio calculation and showed that 12 CO2 and 30 CO2 has a different cross sections. And he predict that the solar type spectrum hit the carbon dioxide. 12 13 CO2 react way faster than 12 CO2. And his estimate is minus 200 per mil because the spectrum is a little bit different. So that's why the fluctuation is maybe much more than we expect. We determined experimentally by using xenon lamp, not the solar sunlight. Okay, so the carbon monoxide could have very negative isotopic composition. And what's the fate of carbon monoxide? This is not the end of the story, because the carbon monoxide is very reactive with, if the system is reducing, react with excess hydrogen atom and making a lot of interesting organic molecules. This is a very simple experiment done by our graduate student, Waka Kawade. And she put the carbon monoxide and water into the flask. And yes, we can see a lot of product, formaldehyde, acetaldehyde, formate, acetate, glyoxylic acid, and so on and so forth can be produced. So the carbon monoxide atmosphere is very, very good for prebiotic synthesis. But if the gas phase is not carbon monoxide, but the CO2, and then nothing happened. Not nothing happened, but as expected, CO2 is photolyzed into carbon monoxide, and then gradually increased, and then started to synthesize this compound. So the carbon monoxide is reducing agent, and also the seed of making the prebiotic compound. So even started from CO2, the system is reducing. In this case, she put the ferrous ion in the water. Yes, and then, yes, we can see the production of the organic material. Even started from CO2, not from CO, by solar-like UV photodissociation photochemistry. Okay. One thing I have to add, if we put some reactive nitrogen species, N2O, and then we can see also ammonia and amino acid can be synthesized. So, okay, CO atmosphere is very nice for prebiotic synthesis. All right, and then this very depleted signal can be transferred into organic material, and this is very tasty, so could be fixed by biology and could be mixed with the organic material. And that's the third hypothesis. If the atmosphere is reducing and reaching CO, some organics, very C13 derived organics can be supplied from the atmosphere. Okay, so I have 3 more slides, it's okay. And the same scenario can be true, maybe applicable to the early Martian atmosphere. Okay, the Martian atmosphere is rich in C13 compared to the Martian mantle. And so the C12, the lighter carbon, might be escaped into space. That is a standard scenario. But if the early Martian condition is very reducing and reaching CO, the part of C12 is converted into organics through carbon monoxide, and then could be deposited in the early Martian sediment. That might the reason why Martian atmosphere, atmospheric carbon dioxide is rich in C13. So this is a summary. So our prediction is, our model is, if our model is correct, we can see very C13 depleted organic material in early Martian sediment. So trying to find that. Okay, so this is final slide. So where is the life originating planet? So okay, the little state is very key, and and we can see some water, the wet condition, and the suitable condition is, for prebiotic synthesis is present. You know, the methane-rich or too reducing condition is not favorable. So no oxygen. So, but now the present day, modern day Earth and Mars is very oxidizing. So we don't know the example of life emerging, condition in our solar system. So I hope the exoplanet people to search for this type of exoplanet. That's my hope. Thank you very much.